When Al and I are talking about light, what we're referring to is the fact that fiber optic cables use pulses of light to carry information, and that's what sets them apart from metal wires that carry electrical signals. Invented by Corning Glass in the 1970s, fiber optic cables are thin tubes of either plastic or glass, roughly the size of a human hair. Fiber works by reflecting all of the light that enters into it along the path of the cable. It's like a hose for light. Light comes in one end and bounces down the fiber until it leaves the other end. The key to making this work is that fiber has a high refractive index. The refractive index tells us how much light bounces off versus refracts through a surface. Here's a quick refraction example. When you look at the surface of water, you can see that some of the light reflects off the surface, but you can also see into the water, so not all the light is bouncing off. The light that passes through the water also seems to bend a little bit. This is because the water and air have different refractive indexes. If you get the refractive index just right, you can make all the light coming in from one direction reflect off the surface of the water instead of refracting through it. And that's the goal with fiber, this state that's called total internal reflection. Every photon that enters the fiber should leave the fiber at the other end, with none refracting through the outer surface. So what makes fiber faster than copper? It turns out there are two main reasons: bandwidth and resistance to interference. Let's get into just what the heck this means. Bandwidth is the total amount of signal that you can put onto a cable at any moment, and fiber has a much greater bandwidth than copper, which means that it's capable of moving more data in any single amount of time. Both copper and fiber transmit electromagnetic signals, which is the stuff that makes up things like light and radio waves. Copper carries radio frequency signals, and fiber carries visible light. The basic unit of measurement for electromagnetic waves is the hertz, representing the number of cycles per second when a radio wave is transmitted. 1 hertz just equals 1 cycle per second. In the best case scenarios for copper, it will have around 2 gigahertz of bandwidth, so about 2 billion cycles per second. Fiber, on the other hand, typically carries signals on frequencies between about 185 to 205 terahertz. That is, 185 to 205 trillion cycles per second. This gives a single strand of fiber about 10,000 times the theoretical capacity of a copper cable. Now let's talk about interference rejection. Basically, interference is about the signal-to-noise ratio, or SNR, which is the ratio between desired and undesired signal on a wire. Imagine that your friend starts to walk away from you while she is talking. Her voice would get fainter, and it would get harder to understand what she's saying as she walks away. Now imagine that a marching band starts marching by as she is talking to you. Again, it gets harder to understand what she's saying. These are examples of the signal getting weaker or the noise getting stronger, either of which decreases the signal-to-noise ratio, which reduces the speed at which we can send information. Metal cables, like telephone wires and coaxial cables, tend to lose signals as they get longer. And they also act like antennas, picking up noise from other radio sources, like radios or other metal wires. But because fiber achieves almost perfect total internal reflection, it loses very little signal, and it doesn't pick up interfering light from other sources. It experiences very little noise and is a very strong signal. All in all, when it comes to raw speed, fiber's advantage over other technologies is clear as glass. Because it has a cleaner signal, it is able to carry much more information than an electrical signal moving through a copper cable.